Edge AI refers to artificial intelligence models running directly on local devices instead of sending data to distant cloud servers for external processing and response generation. In traditional cloud computing, data travels from your device to centralized data centers, gets processed remotely, and then returns with results, introducing latency and network dependency. Edge AI brings computation directly to the device where data is created, allowing information to be analyzed instantly while reducing dependence on continuous internet connectivity. Everyday devices like smartphones, smart cameras, vehicles, and home assistants now include specialized processors capable of executing artificial intelligence inference tasks locally and efficiently. To understand Edge AI clearly, we must distinguish between model training and inference, because edge devices primarily execute inference rather than performing large-scale training computations. Training occurs in powerful data centers using massive data sets and high-performance GPUs, where neural networks learn patterns by adjusting millions of parameters through iterative optimization. After training, a compressed version of the model is deployed onto edge devices, where it applies learned patterns to new incoming data during real-time inference. Inference involves taking real-time inputs, such as images or audio, and producing predictions or classifications directly on the device without external processing. When your smartphone unlocks using facial recognition, it processes your biometric image locally, ensuring quick response times and enhanced data privacy. This local processing depends on hardware components such as neural processing units, digital signal processors, and optimized CPUs integrated within modern system-on-chip designs. Neural processing units, or NPUs, are engineered to accelerate matrix multiplications and parallel computations that form the mathematical backbone of deep learning inference. These operations involve multiplying arrays of numerical weights and inputs, enabling neural networks to compute outputs efficiently through layered transformations. Because NPUs specialize in these computations, they deliver higher efficiency and consume less power than general-purpose CPUs performing identical artificial intelligence workloads. Power efficiency is critical for edge devices since smartphones, wearables, and embedded sensors operate under strict battery limitations. Edge AI models are typically compressed using techniques such as quantization and pruning to reduce memory usage and computational demand. Quantization reduces numerical precision, for example, converting 32-bit floating point values into 8-bit integers, significantly decreasing memory requirements and improving inference speed. Pruning removes redundant neural connections that contribute minimally to predictions, shrinking model size while preserving acceptable accuracy levels. Before inference begins, raw sensor inputs are cleaned, normalized, and structured through pre-processing steps to ensure reliable model performance. A smart camera may resize images and correct lighting conditions before running object detection, ensuring consistent inputs for accurate local inference. Efficient memory management ensures that models and intermediate calculations fit within constrained device RAM without degrading performance. One major advantage of Edge AI is reduced latency, enabling devices to make decisions within milliseconds without waiting for network communication. In autonomous driving systems, rapid on-device inference enables split-second decisions that directly influence safety and navigation accuracy. Privacy improves because sensitive data, including biometric identifiers, remain stored and processed locally instead of being transmitted externally. By minimizing cloud communication, Edge AI reduces bandwidth consumption and lowers operational costs across distributed device networks. Edge systems integrate hardware acceleration frameworks that interact with operating systems to efficiently schedule artificial intelligence workloads. Deployment toolkits convert trained models into optimized device-specific formats compatible with mobile processors and embedded hardware platforms. Frameworks such as TensorFlow Lite and Onyx Runtime provide lightweight execution environments tailored for constrained edge devices. These runtimes manage task scheduling, hardware delegation, and memory allocation to maintain stable inference without overwhelming device resources. Continuous artificial intelligence computation generates heat, making thermal management essential for compact consumer electronics. Systems dynamically distribute workloads among CPU, GPU, and NPU components depending on complexity and energy efficiency requirements. In hybrid architectures, urgent computations occur locally, while aggregated or non-critical data is transmitted to the cloud for advanced analysis. This distributed approach allows centralized retraining while maintaining decentralized inference across large networks of devices. Firmware and over-the-air updates enable devices to receive improved models without requiring hardware replacement. Security mechanisms such as encrypted model storage and secure enclaves protect algorithms and sensitive user data. In industrial environments, Edge AI supports predictive maintenance by analyzing equipment vibrations and detecting anomalies in real time. Retail systems use edge-enabled cameras to monitor inventory levels and customer movement patterns without transmitting raw video streams. Healthcare devices leverage Edge AI to monitor vital signs continuously and trigger immediate alerts when abnormal conditions arise. Smart home assistants process wake words locally, activating cloud services only after confirming intentional user interaction. Because inference runs locally, devices continue operating effectively even during temporary network outages. Distributed edge processing improves scalability by spreading computational load across endpoints rather than centralizing it in massive server clusters. Developers must balance model complexity with hardware limitations to ensure responsive and energy-efficient performance. Testing and benchmarking evaluate throughput, latency, and accuracy trade-offs to determine optimal deployment configurations. Model distillation allows smaller student networks to learn from larger teacher models, preserving performance while reducing computational demands. Semiconductor innovation continues delivering more powerful yet energy-efficient artificial intelligence accelerators for edge applications. Faster connectivity technologies such as 5G enhance hybrid coordination between local inference and cloud-based retraining processes. Edge AI transforms devices from passive data collectors into autonomous systems capable of contextual decision-making.